It is my pleasure to introduce our next speaker, Putin, from the University of Oregon. The title of his talk is Density of Unconditional Gabor-Schauder Frames.
Okay, so thanks for the introduction and thanks for the invitation and thanks for organizing this online conference so that I can be here to share some of my recent progress on some research topic. And today I'm going to talk about the density of unconditional Gabor-Schauder frames. And let me emphasize this talk is actually kind of motivated by a series of work developed by my PhD advisor, Chris Hyle, back to 1990s. So let me begin with some notations and definitions. So assume that G is a non-zero function in L2R and the lambda is a countable subset of R2. Then throughout this talk, we will use this notation G gamma to denote the Gabor system associated with G and the lambda. So what I mean by Gabor system is this sequence M, B, M, T, A, N, G. And here, for any non-zero A, B, MB is just the modulation operator defined by the multiplication by exponential to the 2 pi IBX. So the idea of this modulation operator is like we try to shift the function g not in the time side but in the frequency side. And the TA, will be the usual translation operator defined by TAG of x equals to g of x minus a. So I will use this notation to denote a Gabor system associated with a non-zero function g and a countable subset lambda. And usually this lambda is called the set of time frequency shift because we are kind of shifting the function not only on the time side but also on the frequency side. And the major question we want to answer is the following question. So assume that you have a Gabor system which has some nice approximation property. Then can you say something? Is it possible to say something about the density of the set of time frequencies set associated with this Gabor system? But this question is actually a very broad question in a sense that at first you can define whatever property you like as a nice approximation property. And also you can use some other density criterion to estimate how dense the distribution of this set lambda is in R2. So I'll get to this point what I mean by at first nice approximation properties, and the second how I estimate the density of a countable subset in R2. Okay, so to me, a nice approximation property must be established on the so-called reconstruction formula. So what I mean by reconstruction formula is that we say a Gabor system is admits the reconstruction formula if every element x in L2R can be written as the summation of Cn. Here Cn are some coefficient and times MBM TANG, and with the convergence of the series in the norm of L2R. So as long as this equality is satisfied for all x in L2R, then we say this Gabor system satisfies the reconstruction formula. But the thing is, this property is far from being a nice approximation property because at first we don't have any control over the coefficient Cn, right? So in this case, we might want to have some control over the coefficients in the sense that is it possible to find some sequence Yn in L2R such that every coefficient Cn in this equality can be realized as the inner product of x itself and the sequence Yn. So in this case, we say we have some control over the coefficients. And moreover, the convergence of the summation in this equality here might subject to the order of the summation in a sense that you have to specify what kind of enumeration you're going to use for your Gabor system. And once you mess up the order of your summation, it is possible that you end up with a divergence of the series. So that being said, is it possible to have some sort of unconditional convergence of the series in this equality? No matter how we permute the order of the summation, we still have the convergence and they all converge to the same element. And the third property I'd like to have is it possible to have the uniqueness of the series in this equality? So that means that all Cn here are unique. So so let me first give a name to to low-scalar system which satisfies at least one of these three properties. So we say a Gabor system is a shorter frame for L2R if there exists some sequence Yn such that every element x in L2R can be written as the summation of the inner product of x in the sum sequence Yn and multiplied by m bntang with the convergence of the series in the norm of L2R. So so when a Gabor system is a shorter frame, we have some control over the coefficients, which is the first nice approximation property I just mentioned. And we say a Gabor system is an unconditional shelter frame for L2R if it is in shelter frame. So we have the control over the coefficients. And moreover, the equation 1 here holds with the unconditional convergence of the series in the norm of L2R. So that being said, so you don't have to care like how you sum up, these elements here. You will still have, the convergence and they all converge to the same element. And finally, we say a Gabor system is a Rees basis for L2R if it is an unconditional shelter frame and the series representation here in equation 1 is unique for all x in L2R. So the coefficients must be unique with respect to a given element in L2R. And in fact, to construct an unconditional shelter frame in L2R is a highly non-trivial task. But the thing is, back to 1952, Dauphin and Schaffer, they introduced a very novel notion to construct a sequence that is an unconditional shelter frame. And in fact, the notion they introduced is a much stronger notion than just being an unconditional shelter frame. So the notion they introduced is the so-called frame. So we say a Gabor system is a frame for L2R if there exists some some positive constant A and B such that this inequality here is satisfied for all x in L2R. So surprisingly, once a Gabor system satisfies this inequality, then it would be an unconditional shelter frame, and moreover, it is much stronger than unconditional shelter frame. So one reason I like to to talk about these four notions together is that we have some sort of hierarchical structure in terms of the inclusion relationship between these four families. So that is based on our definitions, we have, Rees bases are part of frames, and the frames are part of, unconditional shelter frames, and the unconditional shelter frames, are part of, shelter frames. So now I can, refine my question a little bit. So as I mentioned, the main idea behind this research topic is we want to see how dense, the set of time frequency shifts can be when we have a Gabor system with some nice approximation properties, right? So now I can refine the question a little bit. So now the question becomes, how dense is the distribution of lambda? Here lambda is the set of time frequency shifts in R2 if this Gabor system belongs to one of these four families, right? But still, I haven't really talked about what kind of criterion I'm going to use to to estimate how dense this lambda is, right? So the criterion I'm going to use is the classic building density. So the lower building density and the upper building density of a countable subset lambda in R2 is defined by these two limit inf and the limit sub. And here I will explain how to visualize these two notions shortly. And here this QHX denotes the square center at x with side length h. So here in the notion of lower building density, we check the limit inf by letting h tend to infinity of the infima of this intersection divided by h squared, right? Where we take the infima over OX in R2. So the idea is that we fix some some square center at some point with the side length h, and then we try to use this square to cover the points. Let's say this block points is the set of time frequency shifts, and we want to see how many points are contained in this square, and then we try to find we divide the number of points by the area of this square, right? And we try to find the maximum average and the minimum average, and then we check the limit sub and the limit inf to find the greatest value we can achieve and the minimum value we can achieve. So this is roughly the the visualization of lower building density and the upper building density. So now this is the criterion I'm going to use to estimate how dense a set in R2 is. So now I can further refine the question a little bit. So now recall that we have this hierarchical structure, right, where we have some sort of inclusion relationship among these four families. So now the question becomes, what can we say about the upper and the lower building density of lambda in R2 if the Gabor system G lambda belongs to one of these four families? Okay, so of course, let me start with the the leftmost family, the Reed spaces. So back to around 1999, Christensen and Dan and Heil, they proved that if we have a Gabor system which forms a Reed spaces for L2R, then we must have the lower building density associated with lambda equals to the upper building density associated with lambda equals to 1. And they also proved that if this Gabor system is a frame for L2R, so recall that frame is a Gabor system, satisfies some sort of inequality. Then in this case, we must have the lower building density being greater or equals to 1, and moreover, the Gabor building density, the upper building density has to be finite. So this is what they proved in their paper. And of course, there are still two questions remain unanswered, right? That is, what would be the range for the upper and the lower building density for unconditional unconditional shelter frames and the shelter frames, right? So let me first talk about the density result associated with shelter frames. So I don't think the following result has ever been explicitly stated in some paper, but the thing is, we know that if a Gabor system forms a shelter frame for L2R, then it is possible that the lower building density of lambda is equal to 0. It could be as low as 0, and the upper building density could be as high as infinity. So let me talk about why it is possible that the upper building density equals to infinity. So let me back to the definition a little bit. So this is how we define a shelter frame. But you can imagine, in fact, we can just add whatever points we like into a shelter frame and then set the corresponding yn to 0. Then in this case, it doesn't really change this equality here, right? But the thing is, we can add whatever points we like into the Gabor system without changing this equality. So that being said, we can increase the upper building density to infinity. And for the lower building density part, it is possible that the lower building density associated with a Gabor shelter frame, as could be as low as 0. The reason is it is possible to construct a shelter frame which only use a pure translate. So recall that in the definition of Gabor system, we use we use some shift on the frequency side, and we also use some shift on the time side, right? So it is possible to construct some shorter frame which only uses the shift on the time side. And when you only use time shift in a Gabor system, then the lower unit density could be as low as 0. So that's why we have this range for Gabor shelter frames. So now the remaining unanswered piece is the part of unconditional shelter frames. So that is when you have an unconditional shelter frame, which is also a Gabor system, then in this case, what can we say about the lower building density and the upper building density associated with such a system? And it turns out when we have a Gabor system which forms an unconditional shelter frame, then still the lower building density cannot be less than 1. So 1 is still a lower bound, just like the case of Gabor frames. And of course, because unconditional shelter frames is part of shelter frames, right? So it is also possible that the upper building density can be as high as infinity. So the upper building density part is actually not that surprising because, as we mentioned, we can add whatever points we like into a Gabor system, and by setting the corresponding element yn to be 0, right? So in this case, we are not changing anything, right? So the surprising part is that still here the lower building density part has to be greater or equals to 1. So now to show the idea of the proof, let me take a closer look how Christensen, Dan, and Heil proved these two density results back to 1990s. And the main idea in their paper was the so-called homogeneous approximation property. So let me explain what this homogeneous approximation property is. So assume that we have a Gabor system G lambda. Then for any A, B in R2 and any R greater than 0, we define WRAB to be the span of MQTPG. So we do some time frequency shifts over this function G, and here PQ is a point contained in the intersection of QRAB. So here QRAB is the square center at AB with side length R. The intersection of QRAB and the lambda. So now we say a Gabor system satisfies the homogeneous approximation property if for each f in L2R and the epsilon greater than 0, there exists some positive R greater than 0, such that for any AB in R2, we have the distance between MBTAF. So we do some time frequency shifts on F, and the distance of MBTAF and this subspace must be less than epsilon. So let me give you a visualization, what this homogeneous approximation property is talking about. So for now, just think of AB is the origin. So here, think of A equals to B equals to 0. So now let me assume that the yellow points are some points from the set of time frequency shifts associated with this Gabor system. So yellow points are just some points from lambda. And now the homogeneous approximation property says is the following. So now assume that AB is just the origin. So now there must be enough points contained in this square so that the distance between F and the subspace generated by these 0 points is small enough, right? And now, but the thing is now no matter how you shift these green points, they say you shift the green point from here, from origin to here, and you use the sine square to cover, or to catch points from lambda. In this case, there must be still enough points, contained in this squared from lambda, so that the distance, between MBTAF and the subspace generated by, these 0 points could be small enough. So intuitively, if a Gabor system satisfies a homogeneous approximation property, then the density associated with this Gabor system should be denser than Lowe's Gabor system, which doesn't satisfy this homogeneous approximation property, right? And it turns out this is exactly the key point, to show the density result. And what they did was, okay, so now we proved every frame, satisfies this, homogeneous approximation property, and they also showed that, the density associated with a Gabor frame must be greater than the density associated with, a real spaces. So in this case, this is how they obtain the lower bound 1. Okay, so now after taking, a closer look at, how they prove their density result, this really motivated me to think about the following question. So the key point is now the homogeneous approximation property, right? So now if we have a Gabor system which forms an unconditional shelter frame, then is it possible that, that unconditional shelter frame also satisfies the homogeneous approximation property? And it turns out the answer is yes. So the unconditional shelter frame does satisfy the homogeneous approximation property, and this gives us the lower bound 1. And this is how we prove the density result. Okay, and next, I want to talk about some application of this density result. So the application I want to talk about is about the so-called Olsen-Zodic conjecture. So this conjecture was proposed back to 1992 by Olsen and Zodic. So what they conjectured was that, now assume that you take some non-zero function in from L2R, and once again you consider an arbitrary countable subset of R, then the sequence of translates G of x minus lambda n can never be a shelter basis for L2R. So here what I mean by shelter basis is those sequences which are shelter frames with unique series representation in the reconstruction formula for OX in L2R. So here, a system of translates is in fact, a spatial case of Gabor system where we don't use any shift on the, frequency side. We only consider, shifts on the time side. Okay, and as far as I know, up to today, this conjecture remains open. But of course, people are making progress along this direction. So let me first present some known result, about Olsen-Zodic conjecture. So in the same paper where they propose this conjecture, Olsen and Zodic, they also proved that such a system of translate can never be a shorter basis for L2R. And Christensen then and Heil, they also proved that such a system can never be a frame for L2R. And recently, it was confirmed by Nealab and Sedishev that no matter what function you take from L2R, this type of system of translates can never be an unconditional shelter frame for L2R. Okay, and I think the closest result, I mean, to a full solution to the Olsen-Zodic conjecture was due to Odell and some of his co-author, where they showed that if G is contained in the intersection of L1R and L2R, then such a system of translates can never be a shelter frame if the distance between any two distinct lambda n and the lambda n is bounded below by some positive number. Okay, so now we have seen a bunch of nice results about how to solve this Olsen-Zodic conjecture, right? But we haven't seen any result, about what kind of subspaces of L2R cannot admit an let's say an unconditional shelter frame of chain states, right? So can we say something about those subspaces of L2R which does not admit an unconditional shelter frame of chain states? So to me, I believe there must be some property shared by the L2R, the overall space and the subspace. And once we find that property, we can say, okay, if a subspace satisfies this property, then it does not admit a nice system formed by just chain states. Okay, so now to proceed, let's take another closer look how Christensen, Deng, and Heil proved their result. So the way they prove their result is that if a couple system, is a frame, then the distribution of the set of time frequency shifts cannot be too sparse, right? So that is the lower Billion density has to be 1. But the thing is, when you try to extend this idea to subspaces, this method kind of completely breaks down because you can easily find a couple system which forms a frame for its closed span with lower Billion density equals to 1 equals to 0. So in this case, being a copper frame for just its closed span, need not to be very dense, in R2. But still, these ideas provide some insight how to say something about those subspaces of L2R that does not admit an unconditional shelter frame of chain states. So let me show you a picture. So assume that the yellow points are just pure chain states, which we are going to use to form a system of chain state, and the black points are some time frequency shifts associated with a Gabor frame. So in this case, because to be a Gabor frame, the distribution of these black points must be dense enough, right? So when we move up, the distance between these black points and the yellow points increases to infinity. And also when we move down, the distance between these yellow points and the black points also increases to infinity. So maybe distance criterion is the right criterion when we try to say something about those subspaces of L2R which does not admit an unconditional shelter frame of chain states. And this turns out to be true. But the thing is, we need the generator to be nice enough. So here we say a function L2R is well localized in both time and frequency if there exists some psi in the Schwartz function such that this norm here is finite. Okay, so now I can present my final result. So assume that N is an infinite dimensional closed subspace of an L2R, and assume that we have a Gabor system contained in N that is three spaces for its closed span, and we also have an unconditional shelter frame for this closed subspace. Then it turns out if the generator phi for these three spaces is well localized in both time and frequency, then there must exist some infinite subset lambda prime of lambda such that the distance here must be finite. And this shows us, for example, if you have a Gabor system generated by the Gaussian function, then it does not admit any unconditional shelter frame of chain states. Okay, so I think I'm out of time. So that's pretty much what I want to talk about for today. Thanks for your listening.
Thank you. Any question to the speaker? Okay, if not, let us thank the speaker again. Our next talk will start in 1 minute.